Hi, everyone. Welcome to Riot's Lunch and Learn series. You have found us, the place where we feature all of Riot's partners. My name is Caroline Griffin. I'm Riot's Director of Operations, and I'm super excited to have John Breitenbach here with us. John is Field Application Engineering Manager for RTI Real-Time Innovations, and he is here today to talk about connectivity for widely distributed real-time systems. Just a couple of quick reminders before John gets us started. We will be recording this session, as you may have heard. This will be posted to Riot's YouTube channel and then shared on the Meetup group where you registered. If you do have any questions, please place those in the chat box and we'll either answer those during the presentation or at the end. And my last reminder is that the best way to view this is in speaker view. That'll give you a nice big view of John's presentation with John on the side. But without further ado, I would like to thank John for being a longtime supporter and RTI of Riot. Super excited to have him back virtually today. So I will hand it over to John.
Thanks, Caroline. It's good to be here. As always, we love participating in Riot events. As Caroline mentioned, we are longtime sponsors of RTI, or of Riot rather. Been going to those events for many years now, probably 8-9 years, probably since just about the beginning. But here today, we're going to talk about communications across for widely distributed real-time systems. And when we say widely distributed, those can be distributed locally within a LAN, or they can go across the public internet, truly across the WAN. And when we say real time, basically we're talking about cyber physical systems that need to keep up with physics speed because perhaps they are doing things like controlling a vehicle or a surgical robot or something in the real world. So that's our focus for today. In terms of an agenda, we will talk about some of the challenges that we face with widely distributed systems. We'll look at a few real-world use cases that some of RTI's customers are working on today. We'll talk about some common communications patterns and flows, as well as some of the fallacies, some of the myths concerning the network and network communications. And these really speak to some of the problems that we have today using some of the IoT technology out there. We'll talk about a wish list. Really, if we could design sort of, wave a magic wand and say what would be the perfect solution for being able to create a connectivity framework that we could use for widely distributed real-time systems, what would that look like? We'll talk about some communication scenarios. One of the challenges with any kind of widely distributed system is that you might have different parts of the system that are tucked away behind firewalls and routers and things like that. So how can we get those systems to discover each other, even as perhaps they're mobile and roaming and their addresses are changed? And finally, we'll talk about the concept of a databus, which is the technology that underpins some of the software solutions that we're going to talk about today. So in terms of distributed systems, there are some unique challenges. At the edge of the network, we might have limited resources, limited in terms of CPU processing time, memory, storage, limited bandwidth, perhaps intermittent connectivity to the network. We might even not be connected 100% of the time. Because these systems that are out on the edge are communicating across the wide area network, they're typically traversing public networks. And that greatly expands our attack surface from a security perspective. So if these systems are able to be accessed and controlled remotely, how do we control security and how do we mitigate risks? As we mentioned, some of these systems might be mobile. We might not know ahead of time what the network configuration is or how we reach particular systems. And so we need some kind of concept of dynamic discovery, particularly when we have clients that are tucked away again behind things like routers and firewalls. And then, of course, our networks are not reliable. And it's actually not even a single network in a wide area application. It tends to be multiple segments of networks that are owned by different operators, that are administered by different administrators. And so the net result, the stack up, is that these tend to be unreliable networks. So how do we deal with that that degraded reliability while we're still trying to maintain communications. And then, of course, these are heterogeneous networks. There's all different segments. Some may be wired, some may be wireless. It's different technologies. We might be on, a high-speed fiber backbone 1 minute and a 5G connection the next minute and a local area Wi-Fi network the next minute. And data needs to travel across all of those while still meeting some of our real-time constraints. So let's talk about some real world use cases. These are all real world use cases that our customers today are using or are creating using this technology. RTI is involved with a couple of hundred different autonomous vehicle manufacturers. Everything from road going passenger vehicles, all the usual suspects that you're probably familiar with. Some more recent startups. As well as folks in non-traditional spaces, like people movers. You might have seen some of those around here locally, even on the NC State campus. But before we get to full level 4 and level 5 autonomy for passenger vehicles on public roads, right? So today we're about level 2, that's what a Tesla autopilot is. And that still requires a human in the vehicle to be able to ready and able to take over full control of the vehicle at a moment's notice. Before we can make that leap to level 4 and level 5 autonomy, which is basically where these cars will do everything they need to do the majority of the time without operator intervention, we have a lot of learning to do, and there's going to be some missteps along the way. And so what's happening right now is they're developing these level 4 and level 5 autonomy algorithms. They're deploying test vehicles out on the road, and occasionally these vehicles run into a scenario that they can't solve, right? The AI in the car, the algorithms in the car cannot solve some of these issues, like a tree down in the road or whatever it happens to be. And in those cases, what the vehicles do is they phone home, they call a friend. And that friend is a human operator at a remote teleop station that might be responsible for managing tens or even 100 vehicles. And basically when one gets stuck, they manually take over, they teleoperate the vehicle, they can navigate it around whatever obstacle is in the way, get it back to a safe location, again, in a sort of structured environment on the road where they can throw the switch on the autonomy and let the vehicle go back to doing its thing. So this is a use case that's very common for anybody working on autonomous vehicles. They almost all have some ability to do some teleop during testing. We see a very similar setup in construction, agriculture, mining. These folks as well are making autonomous vehicles. In these cases, it tends to be because these are, in many cases, dangerous places to be driving a vehicle, particularly in the mining world. And so there's a real push on to make these autonomous. But the same problems apply. At some point, these vehicles, because these are very highly unstructured environments, unlike a road where you have clear lane markings, this is wide open space and something like a surface mine, and it's changing constantly. Every time a truck makes the pass or an excavator picks up a load of dirt, the entire environment changes. And so in these cases, they typically have an on-site operations center that provides the friend for the trucks to phone a friend when they get confused or stuck. And it's the same situation. They will briefly teleop, get the vehicle around the obstacle, and then put it back into autonomy mode. And this basically allows a single driver to command and control multiple vehicles instead of requiring that same highly trained driver for each vehicle. They can actually have one driver that can essentially multitask across multiple vehicles that are running autonomously for the most part. Interestingly, these same design patterns we see in some of our customers that are working on things like surgical robots. The surgical robot industry is exploding. We had many customers in this space. And this is essentially a robotics control application, very similar, in fact, to teleop of a car, except this is teleop of end effectors, right? The surgical instruments that go inside the patient. And typically the way that these systems are architected is that there is a cart that is positioned next to the patient that actually has the end effectors, the robotic arms that go inside the patient. And now the surgeon, rather than being physically tethered to the end of those, for instance, endoscopy rods, or laparoscopic instruments. The surgeon is now actually perhaps across the room, or maybe even another room down the hall at an operator station, which is essentially a glorified game controller almost. It's a lot more complex than that, but basically they have a screen in front of them. In some cases, it provides 3D video from a camera that's inside the patient, so that they can see both the internals of the patient as well as what the end effectors are doing. And they control those end effectors over the network. So they are sending command and control messages over a network down to the robot. The robot is actually driving the effectors inside the patient. Interestingly, these systems also provide haptic feedback. So there are sensors in the robotic arms that if an instrument runs up against, let's say, a bone, and it'll actually provide force feedback back to the surgeon down the hall. And again, all of that is over the network, all happening in real time. And now that they're able to do that successfully locally on a network, of course, people start asking questions like, why does the surgeon even need to be in the next room? Why can't we have, a renowned brain surgeon basically be able to operate remotely anywhere in the world across the wide area network? And these are the applications that folks are starting to look into. But it's not all big machines and surgical robots. We actually have some fun customers that are doing interesting things with augmented reality and virtual reality gaming. If you've seen these immersive user experiences where you go to a place like Dreamscape and you put on a helmet and a backpack, and it's a mix of basically a staged area with some augmented reality with real live props that you can pick up and throw to each other that are mapped into the virtual reality that you see within the headset. And these games actually are sharing data. It's actually not too unlike the surgical robots and the autonomous vehicle teleop, because it is real time. You can literally pick up an actual physical torch. It's not on fire, but something that feels like a torch, and throw it to another player who's wearing a headset. Now they see the virtual torch flying in the air, but it actually, the system is responsive enough that they can actually catch that physical object while only looking at the virtual representation of it on the screen. And so this as well is a mix of sort of local area network connectivity for all the local sensors that are tracking the users and their positions and their heads and their poses, as well as cloud-based assets like the game servers up in the cloud. And then we have folks that are doing simulations across the wide area network in the DoD space, where they are tying, live exercises with real life soldiers into virtual environments and virtual scenarios that are running up in the cloud or remote locations across the WAN. So the one thing that all of these applications have in common is that they all have, a mix. It's a different variety, volume, and velocity of data within the system, right? So some of them have things like cameras and LiDARs that tend to output a lot of data at a very high rate. But mixed in with that data is also very small data, things like commands or GPS data, right? So very small messages. But in the particular case of something like control and command, these are very asynchronous in nature. They're sort of come in when somebody does something, as opposed to something like camera data, which is very steady state. And we might need different reliability for these. So something like a camera, we can tolerate lossy data, and we might actually prefer that. We're much more interested in getting the latest frame out of the camera than getting a retransmit of one that we dropped 10 messages ago and holding up the subsequent 9 in the meantime. So in the case of something like video data or LiDAR or radar, we might want a best effort delivery that puts more of an emphasis on getting the most recent data rather than completeness of the data set. Control commands, error messages, logging by contrast, those are things that tend to be asynchronous in nature. And in those cases, we probably want reliability. We want to make sure that we get every command in the order that it was originally sent without any gaps in the sequence. So reliability is important, and ordering is important for some of the data. There's a big difference between getting a message for, in the case of our DoD customers, open the hatch, fire the missile, if you get those messages in the opposite order, really bad things happen. So in this case, for those types of data flows, it's really important that we have reliability and we have correct ordering. So how do we handle all these different feeds and speeds of data in a system? And typically, if you're using sort of existing technologies, you might end up with a mixing and matching, right? You might get a video library that does streaming of video, and that's one API and one software stack that you have to learn, and it's going to require a particular connection across the network, whether that's UDP or TCP or whatever, but you're going to have to manage it within that one library. And then concurrently, if you want to send some data like control commands, you might do something else. You might nail up a separate TCP socket and write application code that just handles the commands. And then if you want some logging and some message ingestion, because you're going to stick that in some kind of database or logging engine, you might do something else. And so you end up with this sort of Tower of Babel of different libraries that you end up using, different APIs that you end up requiring within your application to handle all these different data flows. And then you've got to manage each of those connections independently, but also in parallel, right? Because they need to kind of work as a set. And as you try and push that data across the wide area network, once you start encountering things like routers and NATs and just the overall wide area network topology, you've got to manage bridging each of those for each of the different technology stacks that you use. And it becomes very problematic. And we see this all the time where we walk into customers and they've got some system that's cobbled together and they're using 3 or 4 different communications libraries that were never designed to work together, and they're sending different subsets of data through each one. So that's not an ideal solution. And the problem is that some of those point solutions, for instance, like a video stack or a particular IoT stack or something like that, many of those fall into the trap of believing some of the fallacies, the 8 fallacies of distributed computing. So this is a list that was proposed by Peter Deutsch back, I think in the 90s out of Sun Microsystems. But it's amazing how many of these fallacies I still find folks subscribing to today. And if you look at some of them, like for instance, number 2, latency is 0, is a really common mistake that people make. And this fallacy is actually one of the reasons, for instance, that you can't use TCP across a very high latency network, because TCP's reliability protocol was written assuming low or 0 latency. And so as you get into very high latency links, something like a satellite link, TCP's reliability protocol will go into a death spiral. It's spending so much time trying to do its ACKs and NACKs and reliability protocol that it's not able to get any data through. Some of these other ones, like 5 through 8, talking about the topology, we touched on it briefly earlier that, as you go across the wide area network, the topology is constantly changing as you roam, as the internet maps itself around different congestion areas. And we're hopping across all these different network segments that are probably administered by all different people. The person that's administering the backhaul from the cell tower is not the same one that's perhaps administering the local area network on the far end of our connection. And they may have their networks configured completely different. Different ports open at different points, different MTU sizes that can cause hidden drops of data that you'll never see. And so, of course, number 7, there's obviously a cost to going across all these different transports. There's speed bumps and tolls all along the way. And that is because of fallacy number 8. The network is not homogeneous, particularly the wide area network today, with the daily changes to particularly the cellular infrastructure. The network is changing constantly. And so we really have to be careful as we design connectivity solutions to ensure that we don't fall prey to any of these fallacies, that we have to assume that the entire network is 0 trust, that it's constantly changing, that the latency could be infinite in some cases, that our bandwidth could be the opposite of infinite. At times it could go away completely. So how do we deal with all that? Well, if we could put together a communications wish list, right? If I could wave a magic wand and say, well, based on all these applications that I've worked on over the years, what are some of the desirable traits that I would want in a communications solution? So certainly I'd want to cover these first two use cases. I'd want to be able to go from a private client like I'm on now, right, in my house, behind on a local area network with a private IP address, sharing that network with multiple devices here in my house. But there is one externally, I can get on the public internet, and perhaps I want to connect to some public server, right? Some kind of platform as a service server, Microsoft Azure, Amazon Web Services, something like that, or any of the IoT platform as a service services out there. So I want to be able to go private to public. Ideally, for some of these, for instance, teleop operations, I want to go private to private, right? I might have a remote vehicle or remote system that is behind a firewall. I myself am behind a firewall on a private network. And how do I get those two private clients where we don't perhaps know the public IP addresses of either or the exposed ports? How do we get those two to rendezvous and learn about each other's network configuration and then be able to share data? We're seeing the proliferation of mobile devices today, mobile applications, certainly road-going vehicles and some of that construction, mining and agriculture equipment are highly mobile. So how do we handle things like IP mobility and roaming? What if my IP address changes as I bounce from cell tower to cell tower or from network to network? We touched briefly on the need for different feeds and speeds of data in our system. Some data we might want to deliver best effort, some might require reliability. We'd also like, second from the bottom here, on individual data flows, we'd like to define a quality of service for them, right? We'd like to be able to say that, well, this flow, this video stream is best effort, but it does have a deadline. I need to get an update X number of times a second, or perhaps something like a GPS sensor. Similar case. In the cases where we are sending large data, we might want to be able to compress individual data streams versus others. No real benefit to compressing, for instance, a command string, which is very short, so we don't want to incur the extra latency associated with going through compression. But for something like a video stream that's going over that same connection, in that case, we might want to compress it. Things like LiDAR point clouds are easily compressible. And so we want to take advantage of that where we can. So looking at basic transports that we have available to us today, like TCP and UDP, you can see each falls short on different requirements, different items here on the wish list. And so that's where we end up glomming these other technologies on top of it, these sort of point solutions. Well, I need a video sharing solution, or I need an audio solution. And so we end up stacking other things on top of this, and then we end up with this mixed bowl of different technologies. Like I said, different APIs, different structures, all kinds of new stuff to learn. So today we're going to talk a little bit about a product that my company has released. So we have for a long time, RTI for the last 20 plus years has been in the business of providing a connectivity framework for real-time systems, typically that are within a LAN. With the release of our Connext Anywhere product this year, we've really focused on some of these wide area, widely distributed systems. And again, mostly this technology was developed at the request of folks that are creating those types of applications that we talked about earlier, autonomous vehicles, surgical robots, gaming systems, as well as some others. But Connext Anywhere checks almost all the boxes. We do support the different communication patterns, private to public, private to private. We fully support IP mobility and roaming. We have multiple classes of quality of service, so we can support both best effort and reliable, as well as a rich set of quality of service settings, things like deadlines and ownership and durability if we want to provide data to late joiners. All of that can go through the same single connection. So you can think of it as one big pipe with a bunch of virtual pipes inside of it. And inside of each of those virtual pipes, we can have entirely different classes of delivery depending upon the data that we're sending. And so at the end of the day, Connext Anywhere is suitable for even doing teleop across the wide area network. So let's look at those two main communication scenarios that we talked about. So we want peer-to-peer communications. In one case, we have a private client talking to a public server, and the other use case is two private clients that are both hidden behind NATs. So let's talk about that first one. And this is a very common use case. This is the use case that you have when you connect from your local laptop up to, Amazon or Netflix or your bank or your IoT platform of choice. You're on a private network. Somewhere out there, there is a server that is in the public cloud. It's publicly accessible. You know the IP address, or you can look it up easily through something like a domain name server. And so this case, it's pretty easy to make the connection up to the cloud, up to the cloud-based servers. The one thing that Connext Anywhere gives you is it does give you, through that single connection, right, a single port through your router, it does give you the ability to have all of those different data streams contained within that. So we don't need one port for reliable data for a TCP connection and a second port opened up for a UDP connection so that we can send best effort data, or even multiple TCP connections, one for this protocol, one for that application level protocol. Connext Anywhere allows you to do that all through a single pipe and a single API. It doesn't matter. It's not like you need a different API for sending video data best effort versus sending commands and controls reliably. So this is the case where we're going directly peer-to-peer. We have, our game player. This is you in your private address, right? You're going to go out through your router across the wide area network, and somewhere out there, there's this public game server that has a well-known public IP address. It's this 50.10 one here. That server may be behind a router, back in whatever data center it's in, but that's kind of transparent to us because it is always statically mapped to have this public address and port mapping to the internal correct mapping to get to the game server. And of course, we can have more than one of these game players connect to a single server, and they all connect through the same ports. So that one's a pretty easy scenario. The second one here is more challenging, though, right? And this is where we have two participants that are perhaps behind. They're both behind firewalls and NATs. They're both on private networks. And so how can we get these two applications to discover each other? So in this case, we have, two game players down here at the bottom, and our desire is to have them share data directly. We don't want to have to make a second hop and go through a relay service or something if we can avoid it, because we want the lowest possible latency, particularly if we are doing something like remote control, we want haptic feedback. And so in this case, we need an extra little bit of infrastructure, and that infrastructure takes the form of essentially a service that doesn't need to run out in the cloud at a publicly known IP address. But this service really just serves as a rendezvous point for the two game clients. So each game client, the first game client comes on, it gets on the network, it knows the public address of this cloud discovery service. And again, this is an RTI product that's part of our Connext Anywhere package. So you deploy this somewhere on the public WAN, could be an AWS instance, a Microsoft Azure instance. Maybe you have your own on-premise hosting where you can provide an external IP address. But basically the client reaches that, and in doing so, the cloud discovery service is able to pick up, the external address and external ephemeral port number that is assigned by the router of your private network. And so cloud discovery service is able to scrape that information and essentially create a directory so that when the second player does the same thing, connects up to the cloud discovery service, the cloud discovery service can now provide the external address and port of player one over to player two, and conversely, you can take player two's information and forward that to player one. So now both players essentially have the information that they need to communicate directly to each other and get the data through each other's NATs. So for those of you that are not familiar, a NAT is a network address translator. And basically, what it does is it converts, for instance, if you're working out of your house, your cable modem or your router has a NAT in it. And essentially, your house has one external address that is visible to the world that is provided by your internet provider, whether it's cable or whatever. And anybody that sends a message to that address, it'll land at your cable modem in the house. And at that point, the cable modem has to try and figure out which machine or device in your house does it need to forward that message to. And that is essentially the job of a NAT, a network address translator. In this case, for this particular scenario, we need a special type of NAT. It's called a cone NAT. It's a little too deep to get into today, but with a cone NAT, basically, we can facilitate this rendezvous at a common service like our cloud discovery service, and then direct tunneling from one player to the other, both on private networks, both behind a NAT, and be able to communicate directly at a very low latency. And so finally, sometimes you don't have, you still have those two players or those two clients, behind a firewall, behind a NAT. They're on a private network, but they're not cone NATs. So they're not going to be able to accept incoming messages from unknown IP addresses and automatically know how to forward them. And so in this case, you might need another piece of infrastructure, something that we call a routing service. And this basically acts as a relay service. So it's a relay from private to private. So player one connects to the routing service, sends its messages there. Player two does the same, and routing service basically forwards the messages back and forth. And this is able to traverse essentially any kind of NAT. It doesn't require the private users to have cone NATs. So we support all three topologies, all three use cases: private to public, private to private, direct behind cone NATs, and private to private through a relay service. And that pretty much covers most of the wide area network scenarios that you're likely to encounter. So this is what it looks like: simplified internal participant one, game player one sends a message up to routing service, which is out hosted in the cloud at a known address, and it just forwards those messages on. And this is a very low latency path. Our routing service can handle hundreds of thousands of messages a second. Okay, so those are the different ways that we can get around things like firewalls and NATs. Let's talk now briefly about security, because as we saw, some of these things like our rendezvous service, our cloud discovery service, are out in the public network. And in the case of our private clients, there are still some exposed ports that people could potentially attempt to attack them through. We've reduced the attack surface by coalescing this all down to a single port, but we still need security. So for the initial handshake connecting to the rendezvous point, to the cloud discovery service, Connext Anywhere supports a pre-shared key type system. And this is a type of system that you would use with basically any of your IoT platform as a service kind of providers. So you have a pre-shared key, you configure that on the cloud-based system, and as long as you hit the server with that pre-shared key, you're allowed to transfer data. Where Connext Anywhere differs from those types of systems, though, is that is just for discovery bootstrapping. That's just our connection up to the individual, up to the cloud service. At some point, then, the cloud service forwards to each participant the IP address and port mapping for the other participants in the system, right? It lets them know what the public addresses and the ephemeral ports for those are. Now, at that point, this second level of security kicks in on the right, and it is a public key infrastructure based security. And this is part of the underlying protocol, DDS's security. And this is a much more robust type of security. So this is you can use a full X509 certificate infrastructure. Critically, what happens here is now the discovery service is out of the way. The participants mutually authenticate. So each participant in the system shares with every other participant that it's talking to its own credentials. It says, here is my identity. And that identity, again, it's an X509 certificate-based public key infrastructure. So all of the clients need to share a common root of trust. They need to all have their identity certificates issued, for instance, by a common certificate authority. And that ensures that even if the cloud discovery service is hacked or attacked or whatever, there's this second layer of protection. It allows you to use the cloud discovery service even for, applications that are connected have different roots of a trust. So a common service can have sort of different enclaves of users that are able to talk to each other. So we have mutual authentication between clients. And then a second phase of discovery goes on after they mutually authenticate, where they actually exchange with each other a list of permissions. And this is another area where Connext is very different from a transport level security. So in a transport level security, right, you connect to a server and you create a secured pipe. And everything in that pipe is treated exactly the same from a security perspective, right? Everything is encrypted. Everything is treated as if it had a need for confidentiality, whether it does or not. And you don't really have a way around that. And so you incur the penalty in both CPU and memory and latency of encryption for every bit of data that you send, whether or not it requires confidentiality. So a common use case in some of these systems is you might send something like weather data, right? And if it's going across your TLS connection, right, some kind of transport level security, you're encrypting weather data for no reason. There's nothing inherently confidential about the weather. Anybody can look outside and see that it's a nice day out. So why are you encrypting that, right? Well, you don't really have a choice with transport level security. DDS security is a little bit different. We can actually define on a per data flow basis. So again, we have that one big virtual pipe. We have many virtual pipes within that. Each of those virtual pipes within it can have their own level of security. We might say, okay, the weather data, we don't need to encrypt that. But, and this waveform of the patient's physiological systems, we don't need to encrypt that. But their critical information that personally identifies that patient, well, for HIPAA requirements, we have to encrypt that. And so I can choose which data flows need full encryption, which can be left out in the open. Perhaps some data flows just need to be authenticated, right? They just need to be signed, which is a much lower bar to get over computationally than full encryption, but it still provides you the ability to authenticate that the data came from a reliable source. And so within this one metadata flow, we have multiple data flows for our different, our radars, our lidars, our video, our commands, and we can apply different security for each of those, including fine-grained read and write permissions within that. So which client can read and write which topics. And so this is a much more sophisticated and secure level of security than just a simple transport level security. Which is important when you're going across the WAN and some of these ports might be exposed publicly. So I've mentioned a couple times Connext and a Databus. And for those of you who haven't been on some of my earlier lunch and learns, we got to talk about what a Databus is. And a Databus is basically a connectivity framework, a connectivity stack. You can think of it as a secure, high-speed replacement for your TCP/IP stack merged with a relational database. And it creates this data everywhere abstraction. And what's cool about it is it doesn't actually, even though it's a data everywhere abstraction, it doesn't actually send the data everywhere to every client. Each application gets only what it's interested in, only what it needs it, only how it needs it. So every application, the applications are represented here by the rectangles on the outside, advertises what its capabilities are in the case of publishing data, or what its requirements are in the case of subscribing to data. So our path planner microservice or app will advertise, hey, I'm interested in the current vehicle pose, and I need to get that update once a second. And perhaps on the left side, we have a position and speed microservice, which actually reads the sensors and publishes the pose, which advertises that, hey, I'm publishing pose and I can offer you the pose 10 times a second, reliably. And so in this case, the offered quality of service exceeds the requested, and so these two applications can actually begin to share data, right? As long as my offered quality of service is greater than or equal to my requested, these can share data. And what's interesting is the applications interface only to the data, right? That's the API. There is no worrying about connections or IP addresses or servers or anything like that. Basically, you express an interest in a particular piece of information and how you'd like to receive it, and then you receive it. And the communications framework, the stack itself, abstracts away all of the differences in CPUs and operating systems and languages, transports. You don't need to be concerned with any of that. So this could be, the position indicator could be a small ARM-based device that's running on an RTOS, and the path planner could be running on some Intel hardware running Linux, written in Java or Python. It really doesn't matter. Those two applications can share data. And so it's an interesting way to think about communications. I spent my whole life worrying about bits and bytes on the wire and sending a message and waiting for an acknowledgement back and timeouts and all of that stuff. And this is a very freeing way to think about communications in a system. The DDS stack really just hides so much of the messiness from you. And so the data itself is the interface. You create an object in C++ or Java or whatever it is, and you basically just say, hey, write this to the middleware, and it takes care of distributing it around the system to anybody that needs it. And conversely, when you need the data, you just say, hey, get me the latest pose, and it just appears in your app as if it had been generated locally. So this shared global data space, it is kind of magical when you start using it and really embracing the data-centric nature of DDS. The other interesting part about this distribution is that it is sort of naturally, inherently, massively parallel. All of these data flows are going on in parallel. They're all peer-to-peer. That's all hidden under the hood. You don't really see it as an application developer. You don't need to be concerned about it. You don't need to be concerned about where this pose information or the steering command is coming from. It just comes to you. So this is a concept, again, called a Databus. It is based on an open standard called DDS, which is short for Data Distribution Service. This is a communication standard that's been around for many, many years, since the early 2000s. It's a very actively growing standard. It's actually a family of standards, very active development, originally designed for real-time control of robots over a network. And so it's grown into all these application spaces like autonomous cars, which are basically rolling robots. And it really is designed to handle all the different feeds and speeds of data that you have in your system. The standard is owned and stewarded by the Object Management Group, the OMG. These are the folks that bring you other standards like UML. They are the largest software standards body in the world. So it's a very well-supported standard. If anybody would like a deep dive separately on DDS and how you can use it to develop smart machines or widely distributed systems, reach out to me after this, and we're happy to give sort of a private deep dive on that. But DDS, I know we always talk about it in terms of connectivity, and certainly that is its main thrust, but I really look at it as a software integration technology. And it really becomes apparent as you start sort of building these sensor to cloud applications. So if we look down here at the lowest level in the lower right, this blue box, we might have a data bus contained within the vehicle or smart machine itself. And that's where we have all our sensors connecting to our actuators, as well as our AI and our autonomy microservices. And they all communicate very high speed, usually an Ethernet backbone in the newer vehicles. But then we want to start sharing some data off vehicle, right? So we go up to the next higher level, our vehicle to vehicle and vehicle to infrastructure layer. And there we might spin up another data bus, which has some subset of the data that's on the vehicle, not all of it. And it might be downsampled in time. And then we can scale up from there up to perhaps fleet management, which again might be some other subset of data, all the way up to some public internet. You're getting the local traffic reports. It's sort of an aggregate of data from all the cars. Now, normally you would need different protocols and different technology stacks at every one of these different levels, right? The guys who are writing the embedded firmware are probably using an entirely different technology than the folks that are writing the web apps. One of the cool things with DDS is essentially represented by this green vertical arrow on the right, is that DDS works at every one of these levels. There are interfaces to RESTful APIs and WebSockets to make, and JavaScript and Python to make your cloud folks happy, as well as all the way down to deeply embedded RTOSs. But there is a common data model across all of this. So you can share the same API, the same interface to the DDS infrastructure at every one of these layers, and the data flows cleanly from top to bottom. You don't need to do any conversion, any mediation between this protocol and that protocol. You know, how do I convert my MQTT down at the car up into something that I can use with a RESTful API for the cloud? All of that messiness goes away. Essentially, you remove that Tower of Babel of all those different technologies, and you can use one stack top to bottom. It's really a profoundly different way to think about software integration, because at the end of the day, it's all about the data. And you know, DDS starts with the concept of data is at the core. Data is the API. Data is the interface between applications. And so integration becomes very, very easy. We see this layered Databus pattern. You know, we showed an example here with smart machines and cars, but we also see it in the medical industry. This same design pattern applies across all kinds of industries. And so in the health world, we might have a Databus, you know, per patient, which ties together all the monitors and infusion pumps and whatever else that are connected to an individual patient. And this allows them to share data in real time, monitor the patient's vitals so that they can do things like throttle back the infusion pump so that we're not starving somebody from oxygen. The individual Databus at a patient can then talk up to a higher level Databus, perhaps at the ward level. We can go to a nurse's station where the nurse can now monitor 10 or 15 or 20 patients. Again, we can go up to a higher level to start to get to the hospital back-end systems, our electronic medical records, our admit discharge systems, and then finally all the way out to the cloud. And again, we have this unified data model from top to bottom. So the same way that we represent a patient here is exactly the same way that we represent a patient all the way up at the higher level. This paradigm, this layered Databus architecture scales really, really well. We've seen this, our largest scale installations are on US Navy surface ships. So things like aircraft carriers, they run combat management system as well as all the other systems on the ship, use DDS in a layered Databus like this, and they scale up to tens of thousands of clients, up to hundreds of thousands, in some cases up to 1 million individual data flows within the system. Each one that can have, again, its own quality of service, its own security, and so on. All right, so I see a question from Jeff. We'll come back to that at the end. So putting this all together, show you, I can't show, unfortunately, this is a new release of software, so we don't have a whole lot of customers that are willing to share videos with it, but because I manage a team full of engineering geeks, they did what all engineering geeks would do. We couldn't get a real monster truck, even though our customers are making these. So one of my engineers, Neil, found this pretty cool remote control RC miniature excavator. And you'll notice there's a purple box on top that's actually a Raspberry Pi. You'll notice a battery pack on top of that to provide power. Looks like he tied it on with his shoelaces or something. And you see some wires coming off. So he's tapped into the servo controls that are on this. And what you can't see behind the arm is that actually a camera mounted on it. It's just, you know, the standard Raspberry Pi camera. And so we built this system up. And then, of course, he powered it on and left it in his backyard and went to the office. And this is connected with our Connext Anywhere. So he is remote behind a firewall at a private IP address. The excavator is remote, obviously, on his home network. He doesn't know what the public address was or or anything. But the remote control app and the vehicle were able to remotely connect, rendezvous at the cloud discovery service, and now they begin to talk directly. And he's able to do teleop control over the network with a live video feed coming back, and you can see it's a mix of data. So we have live video going back. He is sending down teleop commands in order to be able to drive and navigate. He doesn't have great depth perception here because he's only got a single camera. So you can see he ran into the pumpkin. In real life, the large scale vehicles have radar and LiDAR, and they can do some onboard object avoidance. But this is just a sort of simple kind of proof of concept. So anyway, that is what that looks like going across the wide area network. And you can see it's responsive, and we have the ability to get different types of data all through a single connection, right? So the Connext Anywhere, it is going across, it is UDP based, which is inherently unreliable. However, DDS has its own reliability protocol, and that reliability protocol was specifically designed from the get-go, again, for robotic control over a network. So it's a very interesting approach to reliability, very different than, for instance, the reliability that you get with a TCP connection. And it is designed for essentially smart machines, different distribution patterns, many to many, many to one, one to many. So one of the cool tricks that DDS can do is it actually can do multicast, but it can do multicast with reliability, which is kind of unusual. So Connext Anywhere is built on top of Connext DDS, so it does support, it is UDP based. We can get through a single port, provide you all of those different feeds and speeds, but we can do that with reliability where you need it. We support IP mobility and roaming. We support NAT traversal. We can do direct peer-to-peer if you've got cone NATs, and we do support security. Again, because of the underlying protocol, the underlying stack, which is DDS, we do support all the other goodness that brings, but we can now do it across a wide area network. So we do support various communications patterns, pub sub, publish subscribe is really kind of the meta pattern. But we can also support request reply, remote procedure call, and queuing. We have nice features like data caching. So if you're a path planner and you're a late joiner to the network, you don't just want necessarily the current pose of the vehicle. You probably want to know where the vehicle has been in recent history so that you can sort of identify what its current trajectory and velocity is. And so DDS actually provides a capability, a quality of service called durability, that for particular topics, you can say, hey, for this topic, any late joiners, give them the last 10 seconds of my pose or the last 30 seconds or whatever it happens to be. Again, we support fault tolerance. We support redundancy. You can have multiple publishers of the same data with automatic switchover if one of them goes bad. DDS is data-centric. It knows and understands your data types. And because of that, you can apply content filters. So as a subscriber to data, you can say, well, I'm interested in video data from the rear-facing camera, but only when I'm in reverse. Other than that, I don't really care. And you will only get data that meets that criteria, including the ability, in the case of Connext DDS, to propagate that subscriber's content filter across the network and apply it at the publisher, which can save you greatly on bandwidth if we don't even have to put the data on the wire or over the air. The libraries themselves also include baked in a lot of monitoring capabilities. This is particularly critical as you have mobile assets and things like cellular networks. You want to know what's the current throughput. Is my network connection starting to degrade, so that you can perhaps modify your behavior and how you're going to handle that. So the libraries, in addition to providing robust passing of your data, also provide a monitoring infrastructure. And then Connext also provides a complete ecosystem. We don't just provide core communications libraries. We provide a bunch of tools that allow you to visualize your network and troubleshoot it, visualize your data. We have recording and replay features that are fully baked applications that you can deploy with your system if you need something like a black box capability. We have the ability to take our data and put it into something like a SQL database. We have a web integration service, which gives you a RESTful API or a WebSockets interface so that we can push data to web applications. We have interfaces to scripting languages that you might use in that case, like a JavaScript, if you're running something like a Node.js, or if you're writing a browser-based application. And then we also have support for modern languages like Python. So that's what the whole ecosystem kind of looks like. I invite you to, if you're interested in learning more about Connext DDS, feel free to hit our website. We are rti.com. If you go there, I think on the main page, there's a big orange button where you can download an eval. I invite you to connect with RTI on all of our various social media. My contact information is up here in the upper right. Feel free to connect with me directly. I am local here to the Triangle. My email address is johnb@rti.com. You can always shoot me an email. So if you'd like to learn more about DDS specifically, today we really focused on sort of the WAN aspect and the new product Connext Anywhere. But if you'd really like to understand DDS as an alternative to rolling your own over TCP and or UDP or other IoT protocols that are out there, I invite you to reach out. We do these kind of educational, 1 hour intro to DDS sessions all the time, private sessions. So feel free to reach out and take advantage of that. So that takes us just about to the top of the hour. I do see one question from Jeffrey. Can you speak at all on gaming P2P applications, specifically around anti-cheat technologies and tracking data for profiles? I am not a game developer, Jeffrey. I really can't speak to anti-cheat technologies. That's very outside of my level of expertise. For tracking data, I can tell you that you do have visibility into who is connecting, and with DDS Secure, you can restrict that. But I don't know if it's the same level that you would normally have. I know hacking is a big problem in the gaming community. That's something we probably have to talk about offline. I need to better understand your use cases.
Thanks, John. And thanks for the question, Jeffrey. Please feel free to connect with John directly. We'll leave it open for another minute if anybody has any other questions. But as John mentioned, please do stay connected with the free trial of the Connext DDS. Follow RTI on all of the social platforms and connect with John directly. All right, that's all the questions that I'm seeing. John, as always, great presentation. We love your lunch and learns. We appreciate your continued support from you and RTI. This session was recorded. It'll be posted right to YouTube channel and then shared out to where you registered, so you can watch it again. Thanks so much, John. Thanks, y'all, for being with us. We'll see you next time.
Thanks, folks, for tuning in, and thanks, Caroline. Appreciate it.
Thanks, y'all. Bye.
Bye-bye.